identify the polygons from the figures shown here. The shapes shown on the left side are bounded by line segments. They are polygons. On the other hand, shapes on the right side are called curves. They have curved edges. These polygons are further classified as convex and concave polygons. Polygons in which all interior angles are less than 180 degrees are convex polygons. Polygons having one reflex angle are concave polygons. Convex polygons are further classified as regular and irregular polygons. All sides and angles are of equal measures in regular polygons. Let's explore the relation of number of sides and sum of interior and exterior angles in the triangle. Recall, sum of the angles in a triangle is 180 degrees or 2 right angles. Let us take a point O in the interior of the quadrilateral and join this point to all the vertices. We get 4 triangles as shown here. Sum of the angles of these 4 triangles will be 8 right triangles. To find the sum of the interior angles of the quadrilateral, we will have to subtract the sum of all the angles with the vertex O. Similarly, if we take point O in the interior of the pentagon, we get 5 triangles as shown. The measure of the angles of one triangle is 2 right angles. For 5 triangles, the measure of the interior angles will be 5 times 2 right angles. To find the sum of the interior angles of the pentagon, we have to subtract the sum of all the angles with the vertex O from the sum of angles of all triangles. Thus, a polygon with n sides will have n triangles in it, and thus the sum of its interior angles will be found by using this formula. Let us observe the exterior angles for each of these polygons. Let us add up the exterior angles for each of them one by one. We find that the sum of the angles is 360 in each case, which is nothing but 4 right triangles. Can this be extended to any polygon? Let's find out. Recall all the sides and angles in a regular polygon are equal. Sum of the exterior angles in a polygon is 360 degrees. Suppose we have a regular hexagon. How much would be the measure of each of its exterior angles? Since a regular hexagon will have all its angles of equal measures and the sum of all its exterior angles is 360, we can find the measure of its exterior angle by dividing 360 by 6. So how do we find the measure of the exterior angle if we have a polygon of n sides? missing values in the table. Do you see any relation between the number of sides and exterior angles? The number of sides go on increasing as we go down the table. The measure of exterior angle decreases as we go down the table. Thus, we can conclude that the greater is the number of the sides n of a regular polygon, the smaller will be the measure of the exterior angles A. Can you find the missing values? Observe the answers. Observe the values in the table. The measure of interior angle increases as we go down the table. Thus, we can conclude that the greater is the number of the sides n of a regular polygon, the smaller will be the measure of the exterior angles A, and the greater will be the measure of the interior angle. A diagonal is a segment that joins the non-adjacent vertices of a polygon. Any vertex in a quadrilateral will have one non-adjacent vertex. So, there are two diagonals in a quadrilateral. Considering that we ignore the two adjacent vertices on each side of A, we can draw two diagonals, AC, AD. Considering that we ignore the two adjacent vertices on each side of B, we can draw two diagonals, BE and BD. Considering that we ignore two adjacent vertices on each side of C and the diagonal AC already exists, we can draw the diagonal CE. Thus, a pentagon has 5 diagonals. There is a formula that enables us to determine the number of diagonals of a polygon when we know the number of sides of the polygon.
You are familiar with the geometrical figures that have the same base and are between the same parallel lines. Now, from among the figures shown, identify the parallelograms on the same base and between the same parallels. Observe that the two parallelograms ABCD and EBCF in this figure are on the same base BC and between the same parallel lines ED and BC. However, in this case, triangle EBC and the parallelogram ABCD are on the same base BC and between the same parallel lines ED and BC. In this figure, although the two parallelograms ABCD and EBCF have common base BC, they are not between the same parallel lines. Now, what can you say about the areas of the parallelograms that lie on the same base and are between the same parallel lines? Area of a parallelogram is the product of base and height. Now, observe that the parallelograms ABCD and EBCF have the same base B as they have the common base BC. Moreover, they both have the same height h, as both parallelograms are between the same parallels. Therefore, parallelograms ABCD and EBCF have equal areas. Let's verify this result and prove it geometrically. We have seen that when parallelograms lie on the same base and are between the same parallels, they have equal areas. This result can be extended to parallelograms with equal bases as well. That is, the parallelograms with equal bases and between the same parallels are equal in area. But if the parallelograms have equal areas and lie on the same base, then can we conclude that the parallelograms are between the same parallels? Let's find out. You know that the area of a parallelogram is the product of base and height. Parallelogram PQRS and parallelogram TQRU lie on the same base and have equal areas. Now, if the height of parallelogram PQRS be h1 and the height of parallelogram TQRU be h2, therefore, the area of parallelogram PQRS is the product of b and height h1, and the area of parallelogram TQRU is the product of b and h2. But the areas of the parallelograms will be equal only if they have the same heights. Also, the parallelograms will have equal height h if they are between the same parallels. Therefore, the parallelograms with equal areas and on the same base are between the same parallels. Sam has a parallelogram-shaped wooden board. He takes a point on one of its sides. Through this point, he divides the board into 3 triangles. Now, Sam wants to fill these 3 triangles in 2 different colors. The 2 colors which he has are of equal amount. Now, he's a bit confused to decide that which color he should put at what part of the board in order to complete painting of the board with the limited amount of paint. Now help Sam to make the decision. We are familiar with the figures that lie on the same base and are between the same parallels. We are also familiar with the relationship between the areas of 2 parallelograms, as well as the relationship between the areas of a parallelogram and a triangle that lie on the same base and are between the same parallels. Now, do you think there is any relationship between the areas of 2 triangles that lie on the same base and are between the same parallels?